Electrons are fermions, which gives them certain properties that put limits on their wave functions. And in particular, one of the limits is that the wave functions of fermions must be antisymmetric with respect to interchange of those fermions. Now, what does that exactly mean? Let me finish writing this out. With respect to particle interchange. All right, so this is clearly only worrying about wave functions that involve more than one particle. So a single electron wave function isn't bothered by this at all. But the basic idea is this. If I have some wave function, and I'm going to indicate, for example, there's 2 of these electrons in it, so they're represented by these coordinates, that if I were to now switch the positions of these in the function, so now I've got R2 and R1, that antisymmetry means that this is going to be equal to negative. So in other words, when I change these 2 around, I have to put a minus sign in front of the wave function. Now another way we can write this, and maybe a little bit simpler way, is to simply use numbers as our labels for the particles. And so it's basically this antisymmetry is saying that the psi of 1, 2 is negative of the psi of 2, 1. So I want you to understand these now as particle labels. We'll try not to use the coordinates so much anymore. And when I switch their order, I'm basically implying that they are interchanging with one another. So what I want to do is explore what does this really mean for multi-electron systems. So most atoms are multi-electron atoms, right? Only hydrogen has a single electron. So this is going to apply to the vast majority of matter in the universe. Okay, so when I build a wave function for a multi-electron system, we'll use a 2-electron system as our example, but this would apply to any of those. What I can do is I can write this as a spatial part times a spin part. All right, now for the whole wave function, if I have a whole bunch of electrons in there, it can't necessarily be written as a simple product like this. It's going to be a linear combination over products. But for any 2-electron system, I can absolutely actually write it down as a spatial part times a spin part. But let's work on how we put together the spin orbitals for single electron functions. All right, now in the helium atom and in the hydrogen atom, the orbital part that we're mostly talking about is the 1s orbital. Now we could talk about 2s and 3s and 2p and all of those, but we're going to stick with 1s for now just to keep things simple. Now, for me to write this down, what I'd like to do is use a fairly simple notation. I'm going to write 1s for the spatial part of the wave function, and then I'm going to write either an alpha or a beta, and then I'm going to indicate which of the electrons we're talking about. So this is electron 1 in a 1s orbital with spin state alpha. Similarly, 1s beta 1 would be that same electron in a 1s orbital but with spin state beta. All right, so this is now our shorthand for indicating the spin orbitals that we need to combine. And each of these can be rigorously written as a product of a spatial part and a spin part. But the overall wave function may be a little bit more complicated than that. All right, so now when I have 2 electrons, and I'll begin to put this maybe in a little bit different color. If I have 2 electrons, I'm going to label the function 1, but that's not referencing the particles. There might be a couple of ways I could write this down. For example, I could have 1s1, that means particle 1 is in the 1s orbital, the alpha state, and then I might have 1s, another particle in this state, but now it's going to be in spin state beta. All right, so this might represent a combination of 2 electrons, both of them in a 1s state of a helium atom or in a hydrogen atom, and one's in spin state alpha and the other's in spin state beta. And we're not going to make any assumptions about how many can be in what states or anything at this point. But what I will do is say these electrons are indistinguishable from one another. So in other words, we can't really tell the difference between this and this. Okay, the only difference here is I've exchanged particles 1 and 2. I've basically interchanged them. All right, so this is an equally valid way of representing a spin orbital like this. So that means what I really need to do is I need to put these together in some kind of linear combination. And I'll say that I could put them together in a plus combination or a minus combination. And so I'll call the plus combination state 1 and the minus combination state 2. So I'm going to just be lazy and use both of these notations down here to indicate states 1 and 2. Now these aren't the only ones that we could get. For example, what if I set up a third state for 1 and 2 that was simply equal to 1s alpha 1, alpha 1, 1s for alpha 2. Okay, so in other words, I'm going to have both of my electrons in the 1s orbital, and they're both going to be in spin state alpha. Okay, so this is another potentially valid way of writing down my function. Now I can also do this a fourth way by writing this as 1s beta of 1, 1s beta of 2, where both of the electrons are in orbital 1s and in spin state beta. All right, so all of these are possible forms. I've got 4 different possibilities for writing down the spin orbitals for 2 electrons in this low energy helium state. All right, well, let's look at the first 2. All right, so I'm going to write down the last 2. Let's look at these 2 first. Okay, so I could have, for example, for state 3, I may want to reverse, I may want to interchange my 2 electrons. What would that look like? Well, if I take this functional form and write it a little neater this time, I'll have a form that looks like this. But if you look closely at that, well, that's just the same as what I had over here. So in other words, this is just equal to plus the state with the electrons in the original order. Same thing is going to happen when I use the fourth one. If I reverse the order of the electrons, I'm going to have 1s beta 2, 1s beta 1, and that's just going to equal plus the form of the original wave function, this wave function over here. So in other words, these are not, emphasize that, not antisymmetric. Okay, so there's something wrong with these orbitals, and they're not obeying what fermions should do. Okay, for the first 2, I'm going to have, for example, 2, 1 is going to be the sum of these wave functions, so it'll be 1s alpha 2, 1s beta 1, plus 1s alpha 1, 1s beta 2. But if you look at this, this is just the same thing that I've written up here with a plus sign. I've just reversed the order of these 2 terms, but it hasn't changed material of this function. So this is also not antisymmetric with respect to interchange of these. This is just equal to this same function with the electrons in that order. So the only one that's going to end up being antisymmetric, and I think you could anticipate this, is the last one, which is 1s alpha 2, 1s beta 1, minus 1s alpha 1, 1s beta 2, and that's going to be equal to negative of the same wave function with its electrons in the right order. So this one is in fact an antisymmetric wave function, and so it is the one that obeys the rules for electrons. Okay, well, what does that prove for us? Okay, well, only this one is antisymmetric. Does that mean it's the only one that can be the wave function? Well, I've only chosen, for example, a wave function that has two 1s orbitals. What if I use something different? Now, I'm going to have to go to a new page to do this because I want to not write it out so cramped at the bottom. But let's suppose that I had a wave function, and this wave function now would be written like this. And I'm going to have some orbital, I won't specify, for electron 1, some different orbital for electron 2, and I subtract the reverse of these things. Now this is the spatial part of the orbital. Oops. So this is the spatial part. Now I want to combine this with the spin part, and I'm going to do this sort of separately, and again do it sort of quickly. I'll have alpha 1, alpha 2. I could have both of these electrons in an alpha state. This is a symmetric spin state, but I have an antisymmetric spatial state. All right, I could similarly have both of my electrons in beta spin states. Or I could have alpha 1 beta 2 plus alpha 2 beta 1. All of these are symmetric versions of the spin state, and I can combine them with an antisymmetric version of the spatial state and still get an overall antisymmetric function. So what we see from this is that how we combine our spatial and our spin parts matters because of the way that electrons as fermions must be antisymmetric with respect to particle interchange. Now I'll note that in doing this, if the spatial part is antisymmetric, what does that tell me about the spin part? Well, the spatial part antisymmetric occurred here where I had two different orbitals. So in other words, the values of the quantum numbers are different for these two orbitals. All right. In the case of the spins, though, they're either both alpha, both beta, or they're combined in this sort of symmetric way. All right. If the spin is antisymmetric, and this was the case on the other page, in that case, I had two 1s orbitals, so n, l, and m sub l are the same for the spatial part. But the spin was antisymmetric, so that automatically implied that m sub s was different for the spin part. All right, so in effect what's happening here is we can see that I can't have all four of these quantum numbers the same for both electrons. So in effect, what we have is something called the Pauli Exclusion Principle, which I'm sure you saw in general chemistry, but now you've seen a more mathematical reason for why it holds true. And it basically says that no two electrons on an atom can have the same four quantum numbers. All right, and those four quantum numbers are n, l, m sub l, the projection of l on the z-axis, and m sub s, the projection of s on the z-axis. Okay, another way to look at this is that no spatial orbital can hold more than two electrons. All right, so every spatial orbital can have a maximum of two electrons, and that's in fact what leads to the way the periodic table is set up the way it is. Because of the Pauli Exclusion Principle, because electrons are fermions, and because fermions must be antisymmetric with respect to particle interchange.